So today we'll work some more examples of Laplace transforms. And differential equations. And then we'll introduce a function which some of you have seen before. I think I mentioned it in 166 last year. But we'll see how it rises pretty reasonably here. We'll talk about the gamma function. You remember this? Oh. So before, when I taught it in 166, I remember writing it on the board, and you guys all had this stunned look of disbelief that anything like that could be thought up. You know, why would you think about this? But today when we do it, I think we'll see that it's a very natural thing to consider. Let's see. So we need to probably remember our table quickly. So
1 over s.
Okay, and then t to the n was
n factorial over s to the n minus plus 1.
There we go. And s is greater than 0. Note this. What ends is this for? I'll give you a hint. What kind of things can we do factorial? Yeah, we got to use not just any integer, but positive integers, right? Or we could use 0. So that's actually kind of an open question still for us. You know, how? I mean, it's very often that you're dealing with things that are not of the form. I mean, they're of the form t to the n, but n is not a positive integer. Right? For instance, it could be t to the 1/2. Right? So we haven't handled that yet. Let's see. We saw this shift property that came from e to the at. So e to the at, its Laplace transform is 1 over s minus a for s greater than a. And then, more generally, if you multiply any function by e to the at, then the Laplace transform will just be the Laplace transform of f, but you change the variable from s to s minus a. Okay. Or if you like, you shift the Laplace transform. And then at the end of class yesterday, I mentioned sine and cosine, and these I told you I'll leave on the homework sheet, so that's on homework 2. And remember, they're both s squared plus a squared in the denominator.
Sine is
one's an s and one's an a. And
sine is a and cosine.
Sine is a and cosine is s, right? Because sine should be s, but it's not. So cosine gets the s, sine gets the a. Okay. And then we also had formulas for computing the Laplace transform of a derivative. So if you have, for instance, the nth derivative of L, then the Laplace transform was s to the n times the Laplace transform of f. And then you had to subtract out a bunch of terms that were, well, they were powers of s, and then they were initial values of the function. Okay. So I'll write it short as it was the sum. A little better. Okay, I'm sure I can do it better if I'm on this side. There we go. Okay. And they all look like s to the I, and then you take the n minus I minus 1th derivative evaluated at 0. And it should always be that these exponents add up to n minus 1. And so here I goes from 0 to n minus 1. Okay. So I think that's everything we've done so far for Laplace transform. Remind me if I've forgotten any of them. Okay. So what's an example to start with? So let's try to solve the differential equation. Y prime plus y equals sine of 2t. And I'll give you some initial data. Y of 0 is 2, and y prime of 0 is 1. Is it,
0.
oh, that got a little tiny down there, didn't it? Can you read it, or should I make it bigger?
It's f to n minus I minus 1.
Yeah, so I'll blow this up. This is f to the n minus I minus 1 evaluated at 0. There's an s to the I. Should probably write like that all the time. See, Zuen shook her head, and you said, that would be nice. We just need, if you're in Windows, to have that magnifying glass. They probably have it on a Mac too, I guess. That's what we need everywhere. You can just look at the board and, oh, magnify.
Exactly, that'd be great. Like a live screen kind of thing going on.
Exactly.
Sound effects too.
Oh yeah, sound effects would be important.
They need to be in there.
Okay, so how do I go about solving this?
Right.
Well, I could guess at a solution, but that looks hard. Okay. Kaiwei says Laplace transform. What do I want to do with the Laplace transform? It's okay. Speak up, everyone. If you know the answer, go ahead. Zuling, do you know the answer? What would you do? Look through your notes. Okay.
So you do L y prime prime minus plus Ly is equal to L sine 2t.
Okay. So you're applying the Laplace transform to the entire equation. Yep. Okay. And then you're using the additivity, okay, which I guess is something we could write up here. So if you have f plus g, this goes to LF plus LG. And if you have a constant times a function, this goes to the constant times LF. Okay. Okay, so yeah, I apply the Laplace transform to this equation, right? I'm going to transform it. And what you're thinking is it's a differential equation, and the Laplace transform is going to turn it into an algebraic equation. Right? And by algebraic, I mean all you have to do to it is algebra. You're not going to have to do derivatives. Okay, so we get L of y double prime plus L of y equals L sine of 2t. No problem. So, what's L of y double prime? Okay, Kaiwei points. First term is easy. Right? You just raise s to the derivative that you took tau, right? So we get an s squared, and then an L of y. And then we have to subtract off a bunch of terms. And how many terms are you going to have to subtract off? Well, it's always that same number, right? There's going to be 2 terms, right? And you're just going to start decreasing the s. So the first one will have s to the 1, and the last one won't have any s's at all. And then what do you have to put in here? You have to do y of 0. And then what's the last term?
Y prime of 0.
Y prime of 0. Let's see. Does this match our formula, or did we mess up our formula? Let's see. So, it should be the case that, well, this is definitely right, as I've written it. But I'm wondering if our formula is right here. Because these actually, what are these adding up to each time? All right, well, there's no derivative there, and there's one derivative there. 1 plus 0 is 1. There's no s's there, and there's one derivative there. 0 plus 1 is 1. Good, it's always 1 less. Okay, so that's the L of y double prime. Now we need the L of y. Oh, well, that's really easy. It's L of y. And then the last thing we need is sine of 2t's Laplace transform. And that we can rewrite off of the table.
Mm-hmm.
That'll just be, okay, A, what's A? A is 2 over s squared plus 2 squared. So s squared plus 4. Okay, so that is what it is. Kylie?
Just want to verify that the s squared, it's s squared or the second derivative.
Really means s squared. So
Okay.
if it's going to be a derivative, I put parentheses around the exponent. Okay, so as I said, we're looking to make this into an algebraic equation in the sense that we want to just perform algebra. And the algebra we're trying to perform is always to solve for L of y. And of course, the reason we want to solve for it is once we know L of y, we just have to go backwards, right? And figure out what y would give you that Laplace transform. Okay? So let's see. There's just 2 L of y's, so it's pretty easy. You get s squared plus 1 times L of y equals, let me put all these things on the other side. So you have 2 over s squared plus 4. And then you have, well, it'll become a plus s times y of 0. But y of 0 we know. Y of 0 is 2.
Mm-hmm.
So it's just plus 2s. And then minus y prime of 0, which is just 1. Well, the minus become a plus because we move it over, which is just plus 1. Okay, now we don't really want it like this, because what's going to happen? Well, we're going to divide by s squared plus 1, and
Yeah, there's going to get ugly.
it's going to get nasty, right? We want to make sure everything's over the same denominator.
So
So,
multiply 2s plus 1 by
yeah, we
s
better
squared plus 4.
rewrite this as 2s plus 1 times s squared plus 4. And then actually I can put the whole thing over s squared plus 4. Okay, just algebra now. Isn't that nice? See? All that time you spent in algebra working on manipulating fractions and so forth, it's all useful. Okay, and then I have to divide, so I get L of y equals, well, let's see, let's expand this on top after we multiply on the bottom. So we're going to get s squared plus 1 times s squared plus 4. And on the top, we'll get, let's see, 2s cubed, and then 8s, and, oh, an s squared. Let me put the s squared first. And then my 8s. And then I have plus 4 and plus 2 is plus 6. Okay. Now yesterday we had the same problem. We got an L of y which was not in our table. And what did we do yesterday then? We use partial fractions, right? Okay, so this will be a little more interesting because we don't have linear terms on the bottom. So we need to make 2s cubed plus s squared plus 8s plus 6 over s squared plus 1 times s squared plus 4 equal, okay, do you guys remember how to do it when it's quadratic terms? All right, well first, can you factor these
No.
over the reals? Okay, no. So we put these quadratics on the bottom, and what goes on top? AS plus B, exactly. All right. You need to put a linear term on top, and then here we'll use CS plus D. You'll remember in 166, I never liked to use C up there because of the constant of integration, but we don't usually have to worry about that anymore, so. And I feel free. Okay, so let's see, we'll kill everything on the bottom. So 2s cubed plus 8s plus s squared plus 8s plus 6 equals as plus b times s squared plus 4 plus cs plus d times s squared plus 1. Now, it actually will work to use complex numbers here if you'd like to play tricky. Let s be I, so that this would go away, and then you could work all this out, and it'll work just fine. But maybe I won't do this to you. But it's not a bad way to go. It's quite nice. But okay, we'll work it out and then sort it. So let's see here. We have as cubed and cs cubed. So you have a plus cs cubed. And let's see what else. So then you have a bs squared and a ds squared. So b plus ds squared. And then you have a 4as and a cs. So 4a plus c times s. And then you have a 4b and a d. So 4 plus 4b plus d. And what's interesting here is the a's and c's all show up in the same, and the b's and d's show up in the same. So even though it looks like 4 equations with 4 unknowns, it's really 2 sets of 2 equations with 2 unknowns. Okay, so we get a plus c is 2. And b plus d, well, let me skip the b plus d. Let's do the 4a plus c. 4a plus c is 8. And then the second set of equations we get is b plus d equals 1. And 4b plus d equals 6. Everybody agree? Okay, let's see. If I subtract, say, this one from that one, 4a minus a is 3, c minus c is 0. So I get 3a, and then 8 minus 2 is 6. So this one says 3a equals 6, so a equals 2, but if a is 2, then c is just 0. Cool. And this one, I subtract, 4b minus b is 3b, and then the d's cancel, and 6 minus 1 is 5, so 3b equals 5, so b equals 5/3. And if b is 5/3, and b plus d is 1, then d must be negative 2/3. Okay, so what we're actually getting out is that L of y is, okay, a was 2. 2s plus b is 5/3 over s squared plus 1 plus, okay, c is 0 and d is negative 2/3. So I can write this as negative 2/3 s squared plus 4. Okay, so make sure that's what I had. Yep. Okay. So this at least looks a lot nicer. What's y? Can I find these things in my table? So the link says sine and cosine. Elaborate. Which one's coming from sine, for instance?
5 over 3 over s squared plus 1, and then minus 2 over 3 over s squared plus 4. And the further term is cosine.
So what Zuling is saying, there's actually 3 terms here. It looks like 2, but there's 3. There's 2s over s squared plus 1. There's 5/3 over s squared plus 1. And then there's negative, or maybe I'll keep it as like that, negative 2/3 over s squared plus 4. Okay. So there's 3 terms. So let's look at those individually. So if you had L of y equals 2s over s squared plus 1, then what should the y be? 2 cosine t. So yeah, so if the s squared plus 1 tells you that the a is going to be 1, and you can have an s on the top, and that 2 is just a linear term, you can pull it out. So this would give you 2 cosine t. Okay. What if L of y is 5/3 over s squared plus 1? Sure, right? There's no s on top, so it's going to be the sine. A is 1, and so then you're supposed to have a 1 on top. Well, you can put a 1 up there if you multiply it by the 5/3. Okay, there's your 1. And the 5/3 is a constant you pull out. Fine. And finally, if you have negative 2/3 over s squared plus 4, what's your y?
Minus 1 over sine 2t.
Well, let me ask you, is it that?
No.
No. Why not?
Because we need 2 on the top.
Yeah, right? When you have sine of at, okay, it comes from, if you have s squared plus a squared, you need to have the a on top. So we have s squared plus 4, so we need to have a 2 on top. So we can't pull out the entire coefficient. We can only pull out negative 1/3 of it. Right? We would, if you like, we could write this as 2 over s squared plus 4 times negative 1/3.
Could it be negative 2 over s squared plus 4? Can a be negative?
Oh, no, we always are choosing a positive here. Yeah. Okay. Yeah. We'll leave it like that. Okay, so that's our y. So we can put this all together, and we get our y is 2 cosine of t plus 5/3 sine of t minus 1/3 sine of 2t. And you know what's really annoying to me? I was going to guess that. It's a joke. I was going to guess that. Okay. So what's the interesting thing? We started with a differential equation, and we took the Laplace transform of it. We then did high school algebra. all the way to here, right? Think about it. We took the Laplace transform. Okay, this is interesting mathematics. We certainly couldn't teach a high school student how to write L in front of everything. We did high school algebra. And then at the end, we figured out how to read off a table. Yeah, okay, so we've somehow we've turned this very difficult problem of solving differential equations into cookbook mathematics. I mean, you never like to be doing cookbook mathematics when you're a mathematician, but your goal is always to turn everything into cookbook mathematics. It's kind of a strange dichotomy there. Okay. So the next thing is I want to answer this question that I mentioned in the beginning, which is, what can I do to improve this line of the table? How can I compute the Laplace transform, for instance, of the square root of t, right? T to the 1/2 power. So, well, let's see what we do. Well, we can fiddle with this and just see what happens. So we've got to remember the definition. So it's an improper integral, 0 to infinity, t to the 1/2 e to the minus st dt. Note that you'll very often forget this definition because the existence of these tables that we're creating makes it so you don't need to use the definition, right? Which is always the goal. Okay. Yeah. Ideas? Normally we like to use integration by parts, but it's kind of hard to see how things will improve if we do so. Let me try the following substitution. Just to try to simplify things. So I'll try x equals st. I'm doing that just to simplify this a little bit. So if x equals st, then of course dx is going to be, remember we're doing things with respect to t, so this will be s dt. Or if you like, dt is dx over s. Okay. I can do that. Then what about t to the 1/2? What happens if I do that? Well, I could solve for t here. I get t equals x over s. So t to the 1/2 will be x to the 1/2 over s to the 1/2. Right? Assuming s is greater than 0, which we always assume anyway. Okay, so then I would be able, doing all this, I could rewrite my stuff as, well, let's see. Well, first I could say is as far as the limits go, as t, I mean, when t is 0, x will be 0, and when t goes to infinity, x goes to infinity because s is positive. So the limits don't change. T to the 1/2 becomes x to the 1/2 over s to the 1/2, and s to the 1/2 is a constant. Right? I can pull that out if I like. I don't know if I want to, but that's reasonable. So we didn't really change the first term, but now at least. Oh wait, what did I forget? I forgot dt. Right, becomes dx over s, so I actually have to pull out another s. So it becomes 3/2 power. Okay. Now actually, something that just happened there is going to be important for later on. We started with a 1/2 power, and somehow we were introducing a 3/2 power, right? We've increased the power by 1 somehow, and that's going to be useful. Okay, so we've marginally improved this, right? Because now there's no s term in there. we've got the s out. It's well, it's better than when you have an f in there and you have to get the f out. Oh dear.
Oh my god.
Oh my goodness. Okay, so well, the first question whenever you have an improper integral is always got to be, is this thing going to converge? And, well, certainly the square root function is not going to infinity as fast as e to the minus x is going to 0. Right? So e to the x will dominate this conversation. So at least we know this is going to 0, so this has a chance of converging. So as x goes to infinity, x to the 1/2, e to the minus x is going to go to 0. So at least we have a chance. Okay, so now here comes the sort of the kooky part. We're going to prove that this thing is going to converge. Okay, and this is going to be a little delicate. All right. So first recall that we have a nice Taylor series expansion for e to the x, or Maclaurin series. Fine. So if I isolate one of these terms, then e to the x will be bigger than any just one single term. Yeah? Okay, so this is going to be bigger than x to the n over n factorial. So I just chose one term in it. This is assuming that x is greater than or equal to 0. Which is fine because that's what we're interested in, 0 to infinity. Okay, so if I invert this, and invert that, then the inequality will reverse itself. So n factorial over x to the n will be greater than e to the minus x. So if I multiply both sides by 1 over x to the 1/2, nothing will change, right? Because that's positive. So n factorial over x to the n minus 1/2 will be greater than e to the negative x times, well, let me put the x to the 1/2 out front. X to the negative 1/2 e to the minus x. So this whole thing is set up to put an upper bound on this right here, which is, I'm sorry, I want to multiply this by x to the 1/2 there. And then this gets multiplied by x to the 1/2. So that kills some half in the denominator. Okay, so I'm trying to bound this from above by something whose integral is going to converge. Because I know if I have an improper integral,
anything below that will...
and exactly, if this converges, then anything smaller than it will also converge. Okay, so that's why I did all that. So that means that my integral, forget the 1 over s to the 3/2, that's a constant as far as we're concerned. E to the minus x dx. This is going to be, well, I'm going to break this up into two components. The first component is just going to be the integral from 0 to 1. Right? And you'll see in a second why we have to do that. Okay, and I'll call this I1. And then the second component will be, well, 1 from 1 to infinity. Okay, and I'll call this I2. And, well, one thing is pretty clear here. I mean, there's no continuity errors here, right? Everything's defined. Nothing goes off to infinity between 0 and 1. This is just a finite integral. There's nothing bad here. So this is finite. So if this converges, then the whole thing converges. Because, well, if it converges and you add something finite, it still converges. And we know that this is going to be less than, well, I can keep the I1 there, plus, okay, this integral is going to be less than the same integral where I replace this integrand with what we know is bigger than it. Good. So I'm going to get n factorial over x to the n minus a half dx. And right here you can see why I needed to break this integral up. To put this in the bottom, I'm not allowed to let x is not allowed to be 0. So I break it up at 1. Well, that's a reasonable place. 1, nice round number. Well, for being a straight number, it's nice and round. Okay, so I broke it up. The big difference is that, well, at least as long as I put some restriction on n here, I know how to integrate this. You know? So, and hopefully that thing converges. So what's the integral? Okay, well the I1 I just leave. What is this? Well, first the n factorial is a constant. Okay, so you could pull that out if you like. All you're really caring about is x to the, what if you like, 1/2 minus n power. So we can just use the power rule on that. Yeah, so you can do, okay, we have an n factorial. We'll just worry about that at the end. Okay, it's going to be 1 over 1/2 minus n. Add 1 to that, so it's 3/2 minus n. X to the 3/2 minus n. Minus n power, right? Or 1 over n minus 3/2. Any way you like it. Okay? And you have to evaluate it at 1 to infinity, right? Which means we need to take a limit. Good, good, good. So, when is this thing going to converge? I mean, when am I, let me put it another way, when will I not have a chance? Well, if this n is too small, then this will be x to a positive power. If you have x to a positive power, when you put in infinity, right, it blows up. So we don't want that. So we better make n big enough so that this becomes a negative power. So I just need to make n at least, yeah, but greater than 3/2. And well, n here is supposed to be a, right, it's coming from a natural number. So we better make n at least 2. Okay? So let's make n greater than or equal to 2. We can choose any n we like here, so we'll take n greater than or equal to 2. So if we do that, then when x goes to infinity, this whole term is going to go to 0. Right? It's going to die. So it kills everything in here. So all you're going to care about is actually what happens when x is 1. So when x is 1, well, you get 1 to a power, which is just 1. So you get n factorial over 3/2 minus n. And it doesn't matter what this number n is for now. One thing's for sure is it's finite. Yeah, it's a number. So if we in fact take, take n equal to 2, for instance, then what do we get? We get I1 plus 2 over 3/2 minus 2 is over minus a half.
I think it should work.
What's that?
Also, you need to minus and when plugging 1.
Oh, you're right, you're right. I'm sorry, yes, of course, minus it. Yeah. Which is even better because it's going to kill that minus. So you get whatever I1 is, and then plus 4. Okay. Cool. Okay, so that tells us that this integral converges. Yeah? Because look, this integral, well, it's certainly positive, right? And it's increasing, right, as this thing grows, but it's less than I1 plus 4. Okay, so it tells us that the integral from 0 to infinity, x to the 1/2, e to the minus x dx converges. Okay, so it converges to something. Okay, that's good. Tells us we have a chance. I mean, a really good chance. I mean, we need to find out what this is. Okay. In general, this is a fact, and it's such a wonderful fact, I'm going to have you prove it on the homework. If you take anything of this shape, x to the p, e to the minus x, where p is at least, I think, minus 1, this thing converges. Okay, so we just proved it when p equals 1/2. So you just have a few more numbers to check.
Nice.
Okay, and of course, why are we interested in this for arbitrary p? Well, why were we interested in this for, what's the opposite of arbitrary? Specific? Why were we interested in it for 1/2? Well, it's because all we had done was a little, substitution from the Laplace transform of t to the 1/2, right? If I replaced 1/2 with p, then I would know something about the Laplace transform of t to the p, at least when p is greater than minus 1. So this is an interesting integral in its own right because of this Laplace transform consideration. It's so important we give it a name. So this integral is so important. Give it a name. I underline it. It's so important. Okay. So we're going to call this gamma of p plus 1. Okay, and this is really mean to do that. Okay, so we're going to have a new function, gamma. And it should be the case that gamma of p is the integral from 0 to infinity x to the p e to the minus x dx.
Is this the same function in probability? I think in probability.
Yes, the gamma function does show up in probability, and in just a second you'll see why. So historically they've shifted things for some reason. Okay, and we won't go into those reasons right now, but gamma of p plus 1 is defined at p, or sometimes they write it like this. Gamma of p is defined to be the integral x to the p minus 1. Okay, sometimes they write it like that. Okay, so because this only converges for p greater than minus 1, at least at the beginning, the gamma function is only defined when the input is greater than 12. Right? If you put something just slightly bigger than minus 1, then this would be slightly bigger than 0. Yeah? So it should only be defined for positive numbers. There is a process that allows you to define it more generally, even for all complex numbers, called analytic continuation. But we we don't have the time in this class to get into that. In any case, okay, so this is called the gamma function. And, well, we don't know, at least immediately, what the value of this thing is. But at least it gives us a very short way to answer our question of what's the Laplace transform of t to the 1/2. So we wrote down that the Laplace transform of t to the 1/2 is 1 over s to the 3/2 times, well, this is just the gamma function when p is 1/2 plus 1, or 3/2. So the Laplace transform of t to the 1/2 equals 1 over s to the 3/2 times the gamma function evaluated at 3/2. And in general, if you have t to the p, the Laplace transform will be the gamma function at p plus 1 over s to the p plus 1. So where's that coming from? Well, you do, in general, if you have t to the p, you do the exact same substitution. And when you do that, instead of 1 over s to the 3/2 being spit out, you'll get 1 over s to the p plus 1. It's the exact same proof. Kind of.
So what's p?
What's p? So p is going to be anything. Well, what are you allowed to put in, right? Where's our fact? Oh, there's our fact. We're not allowed to have p be anything negative 1 or below. Right? Otherwise, this integral isn't going to converge. Okay? At least the way we've defined everything. So here p is greater than -1. But it's any real number now.
Then what's
What is the difference between t power n and t power p?
Here,
It's the same.
n is a natural number. Here p is any integer. Okay, but there's a really good question here. Wait a second. That has an s to the p plus 1. That has an s to the n plus 1.
Right.
Okay, so that's the same. So the numerators must be the same. Right? So what do you conclude? You conclude, okay, if you put a p here and initially make sure that now p is an n, right? Really a natural number. This would be gamma of n plus 1. So what can we conclude? We can conclude that gamma of n plus 1 equals n factorial. This is, of course, not at all obvious, just by writing down this definition. Of course, you can check it just by using integration by parts and compute that. But this is really nice because this gamma is a continuous function. Factorial, that's just a sequence. It's a function just defined on the natural numbers. So you started with these factorials, which you've always thought as just being defined on the natural numbers. But we've actually produced a function that you can now consider as a real generalization of factorial to at least the positive real numbers. All right, so somebody says, what's 1/2 factorial? Well, before, that didn't make any sense. Now, you can make sense of this. Yeah? 1/2 factorial should just be gamma of 3/2, which we know exists. That's what that fact tells us. Whatever that improper integral evaluates to, that's 1/2 factorial. Okay. So on the homework, not this one, week 2, but on 3, maybe I'll give you a few properties to prove about it. And then tomorrow we'll compute a few different values of the gamma functions that are pretty slick. But by the way, because factorial is shown up in here, you might imagine why this is relevant in probability theory, where factorial shows up constantly, right? Because factorial tells you ways of ordering things, for instance. Okay, we'll see some more connections with probability theory tomorrow.